So this video is on real gases. So prior to this point, we've always talked about ideal gases. And now we're going to get into why we go over and we talk about gases as ideal gases, because real gases make things really messy. So we've talked about ideal gases, and part of the ideal gases and looking at kinetic molecular theory, we say things that particles have zero volume and zero interactions, which isn't true. Right? Particles definitely have volume and they're going to interact with each other. So prior to this, we've done a lot of hand waving that, we're just going to pretend that this doesn't happen so it makes our lives easy. Well, now it's time to actually think about what really happens. So no gases actually behave ideally under all conditions. You can make conditions where they behave ideally sometimes, but pretty infrequently. And to get them to behave ideally, we have to have super high temperatures and we have to have pressures greater than 1 atmosphere. So that means that we're forcing these conditions to happen because we usually don't have things at high temperatures. They're usually at room temperature, and our pressures are usually right around 1 atmosphere because that's atmospheric pressure. So we have to force things from that behave ideally. So Johannes Van Der Waals came around and looked at real gases, and in fact, because of what he did, he earned a Nobel Prize in 1910. So really only 110-ish years ago, this was discovered, which is kind of crazy to think about. It wasn't that long ago. But he discovered and proved that particles do in fact have volume and that particles are attracted to each other. And because he figured this part out, it got named after him. We call them Van Der Waals forces. So he goes on and he says that, volume of gas particles that they have available is less than the volume of the container. So prior to this point, we said, if we're in a 1 liter container, that means that the gas particles have the full 1 liter to move around in because they don't take up space. But in fact, they do take up space, and that means that instead of having the full liter to move around in, they're going to bump into, their friends, the other gas particles, and they really don't have the full liter to run around in. So because of that, volume now needs a correction factor. And to do that, we think about the moles of gases that are in the container, right? So the number of particles. So if there's a bunch of particles in my container, that is going to impact the volume that my container is able to have free for my gas particles to move around. And then that number of moles gets multiplied by a constant that was experimentally determined. And those constants can be found in a table online or in your textbook. So the new pressure that's exerted in the container is a corrected pressure, so we call it P1. And that is equal to nRT divided by my corrected volume. So this came from my ideal gas law, PV equals nRT. I said, I need to make a new pressure because I know in my container, my volume's just not all free space. My particles take up some volume. So I make my correction factor for volume, which I said volume is now volume minus the moles of gas times this constant that was experimentally determined. And so that goes down here. Now because moles are here and then moles are subtracted from volume here, they can't cancel out, which is why this stays. So I divide volume over, and I say my new pressure is equal to nRT divided by my volume minus my correction for the fact that gas particles take up space. So then another part that Van Der Waals proved was that particles do have interaction. So prior to this point, we said particles have no interaction. Wrong. That's not true. They definitely are attracted to each other. And what that attraction involves and looks like, we'll talk about later. But for right now, we just need to understand that they have attractions to each other. So what would strong attractive forces have as an effect on pressure? We can remember that pressure is from collisions of particles with the container. So if we think that there's no type of attraction between particles, they're just going to bounce off each other, no problem, and they're going to move around their merry way. However, if they suddenly have an attraction, that means that instead of bumping into this wall, this particle is going to be more likely to bump into its other particles because it's attracted to them. It's not attracted to the wall. And so if there's a few particles, it's going to be manipulated a little bit by this attraction. But now if there's a lot of particles, it's going to be manipulated even more. So this particle is way less likely to bump into the sides of this container than this particle, because this one is attracted to all 5 of its counterparticles, whereas this one's only attracted to 2 different particles. So the correction factor is going to depend on the particle concentration. So again, we're looking at number of particles or moles of particles. So when we make our correction factor here, that again contributes to why we're going to have a correction factor for our pressure based off of the moles of gas. Another thing that's going to affect pressure is volume. So what would happen to the correction factor if our moles were increased? Well, if moles are increased, right, my correction factor is going to have to increase because my particle is less likely to bump into the sides of the container. So there's more interactions between particles than there would be on the sides. So my correction factor has increased. And then if my volume decreases, so if instead of this whole box, I only have half this box, right, well, that means that my particle A is going to be more likely to bump into the walls just because there are more opportunity and less space for it to move otherwise. So there's going to be some less interactions. The volume increases. That's going to be bigger. And so there's less interactions between the particle and its other particles. So because there's less interactions, there's going to be less attractive forces there. And then our correction factor can be decreased. So our correction factor for our pressure has to do with our moles and our volume, because of what we said here about the number of gas particles and thinking about what happens to our volume. And the reason that it's squared has to do with our number of interactions. So if I have 5 particles, that means particle 1 is going to be attracted to particle 2, particle 1 is going to be attracted to particle 3, particle 1 can be attracted to particle 4, and particle 1 can also be attracted to particle 5. Also, particle 2 can be attracted to particle 3, particle 2 can be attracted to particle 4, and 2 to 5. And then 3 can be attracted to 4, 3 can be attracted to 5, and 4 can be attracted to 5. That means there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total interactions. So that means that there's a lot more interactions just for having 5 particles. If we extend that out to 10 particles, you can kind of see that it's going to get bigger. That particle 1 is going to be attracted to 2, to 3. Thanks, Dave. To 4, to 5, to 6, 7, 8, 9, and particle 10. Then 2 to 3, 2 to 4, 2 to 5, 6, 7, 8, 9, 10, and so on. I think you get the picture. When you add all of those up, you end up with 45 interactions. So this is why we end up with a squared value for our amount here. So condensing this down, we have now altered pressure by saying that our observed pressure is really some corrected pressure minus my constant from my experimental data dependent upon my gas times my moles divided by volume squared. Okay. So this corrected pressure is nRT divided by VNB, which we solved for earlier here. So this, when we sub this in for our corrected pressure, looking at the pressure observed, that means that now my pressure is equal to nRT divided by VNB minus A times NV squared. When we plug this in for our corrected pressure into the ideal gas law and rearrange, we get this. This is Van Der Waals equations. Here, remember that I have PV equals nRT. My pressure we had to edit from here and here. So that ends up with this and this from this equation here. So we've edited our pressure and our volume equal to nRT. This is Van Der Waals equation. So we can look at any of these pressure, volume, temperature, moles by isolating those variables, by looking up our constants, A and B are constants. So we can look up in data tables. And they're going to be dependent upon the gas. Right now in your textbook, it's page 216. You can look those up to figure those out. So if you're solving for one of them, you'll look them up in your book and you'll plug them in. Okay. So in summary, Van Der Waals equation said that at low pressures, the volume of the container is much greater than the volume of the particles. So that trumps it. At high temperatures, the particles are moving fast enough to overcome the attractive forces. So because of these things, we can use the ideal gas law, but otherwise, when those aren't in play, we have to go back and use Van Der Waals equation because we're using real gases.